So this is the second video, the second part to the graphical and linearization techniques, and this one looks in particular at using the process of linearization to determine a non-linear relationship. And so to do this, I'm just going through some examples. These are our typical non-linear relationships. The distance fallen with the time elapsed. If you drop a ball, for example, as time elapses, the distance fallen is non-linear. In other words, it increases more than... It doesn't increase linearly. So if you double the time, the distance fallen is much greater than double. The relationship is actually quadratic as predicted by one of the equations of motion. This is the equation of motion. X is v naught t plus half at squared, or for the IB guys, S is ut plus a half at squared. So if we did an experiment and we varied, for example, the distance fallen with the time, and we plotted distance fallen on the vertical, time on the horizontal, we get a quadratic relationship. But in physics, in the scientific method, we don't assume that we know the relationship, although if we plot that, we get what looks like a quadratic. A graph that looks like a quadratic doesn't mean it's necessarily quadratic, because there are several graphs that look like quadratics that are just similar mathematical relationships. So the process we go by is to basically manipulate the equation, and then we plot the variables to make the variables that we plot, make it so they're linearly related. If we have a straight line graph, there is only one kind of straight line graph, the graph of the form y equals mx plus c. And so these are some relationships here that are non-linear. Speed of a satellite as well here. If we look at that, we can derive that by equating fc to fg, and we end up with the velocity of the satellite being root gm over r. The acceleration of the circle moving at constant speed, with the radius constant, the acceleration then varies according to v squared over r. Okay, let's carry on here. So this first relationship is just a random one I came up with. You might be able to spot the relationship between A and B. These aren't necessarily physical quantities, it's just a mathematical example. So if we plot B versus A, B on the y-axis, A on the x-axis, we get a curve. Looks a bit like a quadratic, or maybe a cubic, or some people would say exponential, but exponentials don't pass through the origin. Looks like a kind of power graph. You might guess the relationship, but if you had a practical relationship, you wouldn't get nice numbers like this. So we can describe that relationship, but physics says, okay, so we can describe it. We think it's probably quadratic. We could quite easily check that by looking at the data, but if we look at a general pattern and we think it's quadratic, either because it looks like an x squared graph or because we've got some research, then we can test that. So we think that maybe b is something times a squared, that's a quadratic. And so what we do is we plot, if we think b is something times a squared, we plot, instead of b versus a, we plot b versus a squared, because b is effectively something times a squared. Plot that against a squared and we get the constant that connects them. If we plot b versus a squared like this, we get a graph, instead of b versus a, which is a quadratic graph, we plot b versus a squared and we get the line of best fit is y equals 2x, which is telling us b is 2a squared. So it was a correct guess. Plotting b versus a squared proved the relationship. B is something times a squared. It found that something because it's the slope. Maybe if you look at the graph underneath here, the table, you can see that. So here we have a, here we have a squared, and if you look at b, it's always double a squared. So the idea is then that to test a relationship where if the theoretical relationship is b equals 2a squared, we can test that against experimentally measured data. We simply plot, instead of b versus a, we plot b versus a squared. B is just the y variable, a squared is the x, we've got y equals a constant times x, which is a straight line graph through the origin. Here's another one, getting a bit more complicated this time. This graph could be anything. It looks like maybe an exponential decay graph. It could be a like y equals 1 over x graph. So it's very hard to say what that is without doing some research. So in physics, we'd nearly always have some research. So if the research suggests that maybe it's we're expecting the graph to be of the form b is a square root of a constant divided by a. So what can we do there? Basically the process involves splitting up the theoretical relationship so that we've got the constant separate from the variable. So the variable is a. Constant divided by a is the same as constant times 1 over a, and we can split the root because the root of a constant times 1 over a is the root of a constant times the root of 1 over a. This is now of the form y equals a constant times x. So we plot b as our y variable, 1 over a as our x variable, and if that relationship is true for this data, we should find a straight line through the origin, and the slope will give us the square root of our constant. Do that, there we go. So we get a perfect line through the origin, which says that basically b is 1.5811 root 1 over a. And if you compare that number with the proposed relationship, which we have as root of a constant, so the root of a constant is 1.5811. That means the constant is 1.5811 squared, which actually turned out to be exactly 2.5. So that's another example. So I'm going to go back to this now and look at this and say, okay, so if we're testing the relationship between x and t with a constant, it's important to realize that a is constant because we might be changing a, in which case we'd have a different problem. But if we're keeping a constant, like for example dropping a ball, then we plot on our y-axis we plot x, which is the displacement. On the x-axis we plot t squared, and we've got then a graph of the form y equals a constant times x, where x is t squared, y is x, as in displacement. There we go. The slope would therefore be 1 over a. Not 1 over a, half a rather, the constant in front of the y variable. Okay, you should try this one. Pause if you want to think about it. So what would we plot here to test the relationship between v and r, to test the relationship that we think is of the form v equals root gm over r? That's theoretical. If we practically vary r and measure the speed required to maintain a circle, this is what this is, then what would we plot? Yeah, so we plot v on the y-axis, we plot 1 over root of 1 over r on the x-axis, and this, it would be confirmed by a straight line through the origin, and the slope would be the square root of gm. So to find the constant g times m, we would square both sides. So gm would be the slope squared. We could then find the theoretical mass of the planet by dividing by a universal constant of gravitation. Here's the final one. A is v squared over r. So if we keep I think that should say actually keep v constant. We can't have a relationship with 3 different variables. So that, I'm sorry about that. I should say with v constant. So if a is v squared divided by r, v is constant. What would you plot to prove that relationship, to validate it? So what we're doing here is we're varying the radius of a circle. It could be, for example, a car travelling in a circle, always going at the same speed, but we change the radius and we find out the acceleration on the car. We could do that using an accelerometer, or maybe figuring out the force and then dividing it by the mass. So what would you plot to verify? You'd collect radius data, same speed squared, and then measure the acceleration. Yeah, you'd plot a on the y-axis versus 1 over r on the x-axis, because this is of the form y equals mx plus c, where y is a, m is v squared, x is 1 over r, c is 0. In physics we're nearly always dealing with just y equals mx, and we don't normally have an mx plus c format. And as it says here, the slope then would be v squared. Summary then for this process, testing a relationship against a guess or the suggested theory. This is why we use linearization, and we can use it to determine constants. Once we've got a straight line graph, the slope of that graph takes into account all the data and will give us some kind of physical constant. There's a bunch of stuff here, just the method which you should be aware of. So you first decide which variables are constant and which are variable, which quantities are constant, which are variable. We make the subject of the equation should be a variable because it's our y-axis, which is going to be variable. We take the theoretical equation, separate out the right-hand side the constants and the variables. We then compare with the equation y equals mx, because we should find that we can write this some physical quantity squared or divided by 1 divided by whatever that y happens to be. We should have that is equal to a constant times whatever x happens to be. So x could be some combination actually of variables, as long as we know and we can measure them. We then, as I said, that says the same thing. Y and x can be any combination of known variables. We plot the combination making the y versus the combination making the x, assuming we can write it in this form, the theory, and we want to test that theory, and we get a straight line through the origin confirms that that's true. The first variable, which comes from one or more variables, is equal to a constant times the second variable. And then a straight line confirms that. The slope will give us the combination of constants coming to make up the slope of the graph then. That's the end of that one. I hope that was useful.